In this section, we will look at pressure, volume, temperature, and number of moles and how those relate for gases. Now, we'll be looking at these in the form of individual laws, Boyle's law, Charles' law, and Avogadro's law that relate just two of those aspects each, pressure, volume, temperature, volume, and moles. There's one that kind of combines the three from here, pressure, volume, and temperature, known as the combined gas law. Eventually, however, we'll be relating all four of those from these laws into something known as the ideal gas law. So just a little caveat as we're going through this section. The point of this section is to show individual relationships when all other things are held equal for a gas. These are important, but know that don't worry about trying to memorize each individual law, because once we get to the ideal gas law, which is in section 11.8, it will relate all of these things into one law. And if you know the ideal gas law, you can derive any of these quite easily from that one law. So again, don't panic or worry about all the different formulas here. Just know these are all getting tied together eventually in something known as the ideal gas law. All right, so the first one is Boyle's law, and it relates pressure and volume. Now, the pressure of a gas sample depends partly on its volume. So how do those relate? Well, if you think about what would happen if you took, again, we'll be using balloons a lot in this. If you had a balloon and you increased the pressure on the balloon, what would happen to the volume? All other things being equal, if you could apply equal pressure all the way around that balloon and squeeze it, it would get smaller. It would decrease. So if the temperature and the amount or number of moles of a gas are constant, you're not changing the temperature, you're not changing how much gas is in your sample, your balloon in this case, the pressure of a gas increases for a decrease in volume and vice versa. All right, so if I have a balloon here and I start applying greater pressure onto it, okay, again, not changing the temperature, the number of moles, my balloon is going to get smaller. So pressure increases, volume decreases. Another example that they give in the book is that of an air pump. Okay, so if you're using a pump like you would use to inflate a bicycle tire. So on the upstroke, as you pull up on it, the increasing volume causes a decrease in the internal pressure inside of the cylinder. Okay, so if there is a decrease in the pressure, as long as it's not close to the atmosphere, there's a valve down here that allows air to come in. It will draw air into the cylinder in order to account for that drop in the internal pressure. And then as you press down, okay, that increases the pressure by decreasing the volume, and then that is allowed to travel through the hose and into your bicycle tire or whatever tire you're trying to inflate. All right, so the relationship between volume and pressure is named after Robert Boyle, who's the one who discovered the relationship. Again, keep in mind right here, very important, constant temperature, constant number of gas particles, which is same as constant number of moles. All right, so the relationship here is that the volume and the pressure are inversely proportional. Okay, so if you see right here, this symbol means proportional to. We're not saying equal to, we're just saying proportional to at this point. We'll use equal a little bit later. Okay, but here's your relationship right here. The volume is inversely related to the pressure. That just means that if one goes up, the other goes down. They don't go in the same direction, they go in opposite directions. Another example, if I have a J tube, just a tube in the shape of a J, it is sealed at one end, it's only open at one end, and I put a liquid sample in there, and I have a certain amount of gas that is at the end of that. If I increase the pressure, the volume will decrease, okay? So the difference in the height in the tube is smaller. Okay, if I add more of the liquid, in this case mercury they're adding here, if I add more to it, okay, it increases the pressure. It's going to decrease the volume right here of that gas. And another way to look at it graphically, if I look at the volume versus the pressure in this chart over here, you can see how it drops. Okay, now notice, volume decreases, and it's an exponential relationship. It's not just a one-to-one linear relationship, which is why we say it's proportional. We don't say it's equal to, although we can, to a certain extent, do that. All right, going back to that idea of kinetic molecular theory. Okay, how can we use that to explain, the observed change in pressure that we see in that previous example? If the volume of the gas sample is decreased, then you have the same number of gas particles, but we've shoved them into a smaller space. They're more crowded. And if they get more crowded, just as if you had people on a dance floor. You have a big dance floor, a lot of space for people to move around. They're not going to bump into each other very much. But if suddenly you had to take that same number of people dancing and, they need to use the other half of the room for something else, so we're going to move you all over to this half of the room and only dance in this space, there's much less space for them to dance. They're going to start bumping into each other. Same thing with these gas particles. They're crowded into a smaller volume, a smaller space, so they collide more often with the walls of the container, with each other, and it increases the overall pressure. Now, we've talked a little bit about scuba divers in the face-to-face lecture portion. Scuba divers know Boyle's law. It's important to them because it explains why it's too dangerous to ascend quickly from a depth. Now, scuba divers use a pressure regulator to deliver air at a pressure that matches the depth that they're at. Otherwise, they wouldn't be able to inhale the air. If you think about it, there's a certain amount of pressure in their lungs. There's more pressure as they go down underwater. So it has to match for that air to be able to go in and out and in and out. So if a diver is at a depth of, say, 20 meters, 60 feet, the regulator is going to deliver air at a pressure 3 times that on the surface, 3 atmospheres. Okay, 1 atmosphere is due to normal atmospheric pressure, and then there's 2 additional atmospheres that just come from the weight of water at the 20-meter depth. Okay, so if you're at the surface, you've got a pressure of about 1 atmosphere. You get 20 meters down, you have a pressure of about 3 atmospheres. So the regulator is going to adjust for that. All right, so the diver that's at 20 meters has 3 atmospheres of pressure on them. They're breathing air that's been pressurized to 3 atmospheres. If that diver decides to suddenly, very rapidly ascend to the surface with their lungs full of 3 atmosphere air, what's going to happen? Well, you're decreasing the pressure. It's inversely proportional. Volume's going to expand. His lungs are going to expand catastrophically as the external pressure drops from 3 atmospheres down to 1 atmosphere. That gas suddenly is going to spread out to take up a lot more space. That is not what you want to happen. That's not a good thing. Okay, so that expansion would be, proportional to the change in the pressure. So if the pressure decreases by a factor of 3, the volume is going to increase by a factor of 3. You can imagine your lungs only have a certain capacity, so if you don't, if it's not enough to kill the diver, it certainly would be enough to do serious damage to the lungs. So they don't want to come up quickly. They want to ascend slowly and keep breathing continuously. As they do so, the regulator continues to adjust to the change in pressure. So it slowly changes the air pressure in their lungs back to 1 atmosphere by the time they reach the surface. Now, there are other reasons for that, too, about gases dissolved in the blood, that you may be familiar with the idea of divers having the bends and whatnot, and that has to do with solubility of gas in a liquid. And that was something we talked about in a previous chapter. All right, so an example of Boyle's law, I'm not going to work through this, but you can just see if you have an initial set of conditions. So you have something starting at 4 atmospheres with a volume of 6 liters, and all else being equal, the temperature's not changing, the number of particles isn't changing. What would happen if we changed the pressure from 4 atmospheres to 1 atmosphere? So it's just a simple relationship. If these are inversely related, pressure and volume, then the pressure times the volume that I start with will be equal to the pressure times the volume that I end with. I know this seems a little counterintuitive, but inversely related means that you're going to multiply them together to relate them that way. All right, so we need to find the new volume. Well, just looking at it on the surface, if I'm going from 4 atmospheres to 1 atmosphere, so I'm decreasing the pressure, we know they're inversely related, so I would expect the volume to increase. Just keep that in mind as you're doing these. Does the answer make sense? So the relationship that we use, pressure times the volume that I started with is equal to the pressure times the volume that I end with. All right, so I solve for V2. Now this looks probably very similar to dilution calculation that we did. Just keep in mind this is pressure and volume for gases, not concentration and volume for liquids. But when I do this, I find that the volume goes from 6 liters to 24 liters, which goes along with what I expected to happen. I expected it to increase, and indeed it did, and it increased by a factor of 4, which is what the pressure decreased by. It decreased by a factor of 4. So, makes sense. That's all good. Just a fun little side note that your book put in there about extra long snorkels. So if you've ever seen episodes of the Flintstones, old cartoon that was on featuring Fred Flintstone and Barney Rubble, and there were several episodes where they would go snorkeling, either getting away from somebody or for a variety of reasons. And they would take really long reeds that would stretch from the surface of the water down to many meters of depth where they were. And then they'd swim around in the deep water while breathing air through these extra long snorkels. Okay, and so the question is, is this realistic? Would this work? If that worked, why would anybody bother with scuba diving equipment other than just having a very unwieldy snorkel? But instead of scuba diving equipment, what if you just had a really long snorkel and you didn't have to pressurize the gas and all that? Well, if you had, let's say they were at a depth of 10 meters again. Well, they have a pressure of 2 atmospheres, so that's going to compress the air in your lungs to a pressure of 2 atmospheres. That snorkel isn't doing anything the pressure regulator would do for scuba. It's not matching the pressure. So if the diver were trying to change the difference, he's at 2 atmospheres of pressure on his lungs, the air he's trying to breathe in is at 1 atmosphere, what that's going to do is force air to flow out of his lungs, not into him, and he wouldn't be able to breathe at all. So think of it, if there were a balloon at either end here, what would happen? Well, this balloon has more pressure. It's going to get squeezed in, all the air is going to get pushed out, and this balloon on the top is going to get bigger. The one on the bottom is going to get smaller. So, not a possibility. All right, the next law is Charles' law, and it relates volume and temperature. So if we think about, for instance, a hot air balloon, if we want to make this cloth balloon, this cloth sack, rise into the air, we use heat. We just apply heat to the air, we get it hot, and it rises. It fills the balloon and it causes it to rise. So why does hot air rise? Well, this is because the volume of gas sample at a constant pressure is going to increase with increasing temperature. So these are directly related. If temperature increases, volume increases. The gas expands. Now, as long as, again, everything else remains equal, the pressure doesn't change and the amount of gas doesn't change, the number of moles, then warming a gas decreases the density, increases the volume. A lower density gas is going to float in a higher density gas, just like wood floats on water. The lower density is going to be on the surface. Okay, so if I heat the air in the hot air balloon that I was talking about, it expands. Its density decreases compared to the air around it, the cooler air, and the balloon will start to float. All right, so if I keep the pressure of a gas sample constant and the amount of the gas constant, and then measure its volume at a number of different temperatures, I see the following relationship. Okay, so if I'm starting here at a low volume and a low temperature down here at the bottom, and then I start increasing the temperature, and I see that the volume increases in a nice linear fashion. It just rises. All right, so volume of a gas increases linearly with increasing temperature and decreases linearly with decreasing temperature. This is very handy that not only do they increase together and decrease together, but they do so linearly in a straight line relationship, because this allows us to predict one very important property of matter by carrying out what is known as an extrapolation. All right, so going back to the previous slide, if these were the measurements, see the dots up here, these are the measurements that we took. And let me switch to red here so we can kind of see what's going on better. I took these measurements, but I can fit the line, and then what I can do is say, okay, if there's a line that fits this data, let me bring that line back past my data all the way to where it intersects this temperature line and the volume. I can keep going out here. Now I don't have the rest of it drawn here, but if I keep going until my data intersects the temperature point, this allows me to see at what point do I get no temperature whatsoever, absolute zero of temperature in terms of Kelvin. Remember that we want to look at things in Kelvin. Okay, Kelvin is related to the energy or movement of particles. So what I want to know is, where is it where I have no energy, no movement of particles whatsoever? That is known as absolute zero. And if I extrapolate backwards, I can see that a gas should have zero volume at a negative 273 degrees Celsius, which is 0 Kelvin. Okay, absolute zero. Now, our extrapolated line shows that below 273 degrees Celsius, the gas would have a negative volume. And that's just not possible. You can't have a negative volume. You can have a zero volume, but not a negative volume. So for that reason, 0 Kelvin is absolute zero. That's the coldest temperature that can possibly exist. Anything colder cannot exist. And to be perfectly honest, at this point, we're not even sure 0 Kelvin. It is a theoretical term. No one has ever been able to reach it. The lowest we've been able to get is about 4 Kelvin. And that's just because of the motion of particles, the interaction of electrons within the atoms. The electrons are always moving. And so that corresponds to a certain amount of energy. So the lowest we've ever gotten is 4 Kelvin. Now this comes from J.A.C. Charles, a French mathematician and physicist who was the one who quantified this relationship. So thus the law is known as Charles' law. It assumes constant pressure, constant number of moles of gas. So what we have is that volume is directly proportional to temperature. So again, notice I'm not saying equal, they're just proportional to one another. Okay. If I want to set equalities, then I have to take that proportionality and relate it to another set of conditions. All right, so if two variables are directly proportional, then increasing one by a factor increases the other. So it's when I want to say condition 1 and condition 2, I'll be looking at a division, and you'll see that in a minute. But previously we said that pressure times the volume in the first condition was equal to pressure times the volume in the second condition. This time we'll be doing a division. So if we double the temperature of a gas sample, now in kelvins, this is going to be the big thing. Anytime you're dealing with temperature for gas laws, make sure you've got kelvins. Nothing else works. Okay, if I double the temperature, the absolute temperature, I double the volume. If I triple the absolute temperature, I triple the volume, so on and so forth. Okay. Now, this follows from the kinetic molecular theory as well, based on the movement of the particles. If the temperature of a gas sample is increasing, that means I'm putting more energy into the particles. They're moving faster, and I can't change the pressure. I have to keep the pressure where it is. I have to keep the number of collisions the same. So to do that, I've got to give them more space because they're moving faster. So I have to space them out a little more. So volume has to increase if the temperature increases, keeping the pressure the same. All right, so again, let's go back to our ever-present balloon here. And if the temperature is changed when I move a balloon from an ice water bath to a boiling water bath, then the gas molecules inside are going to move faster due to increased temperature. So here the idea is that the balloon is allowed to expand and contract with volume in order to maintain a particular pressure. Now, if the external pressure on the balloon remains constant, the volume changes when the molecules expand, when they get hot, and just start occupying a greater volume. If you've ever seen a demo where people put balloons into something very cold, such as liquid nitrogen, you'll see that it works the other way as well. You take a relatively hot, quote, hot room temperature balloon, you put it into liquid nitrogen, which is extremely cold, and the volume then decreases in order to maintain that same pressure, to equalize that pressure from inside and outside. All right, so here's the expression that relates volume and temperature during a change. Temperature change, volume change, or whatever. Okay, so the volume divided by the temperature of the initial condition is equal to the volume divided by the temperature of the new condition that you're looking at. Okay, right here, this assumes that A, the pressure and number of moles of gas are constant, and B, all temperatures must be expressed in kelvins. Okay, I cannot emphasize that enough. There are always so many people that start working these problems and work in Celsius because that's what they've gotten used to working with in other problems, and then suddenly they start getting really wacky numbers. And that's because Celsius is a relative temperature scale. It is not absolute. These are based on absolute temperature, must be kelvins. So if you are working a gas law problem, the very first thing you should do is sit down and convert all of your temperatures into Kelvin. Here's another example. Again, not going to work through it, but they give you a case where you had a sample of gas that was at 2.80 liters at some unknown temperature. We don't know what the temperature was. And then we take it and we submerge it in ice water at 0 degrees Celsius, and the volume decreases to 2.57 liters. Okay, what is the initial temperature? What temperature did we start at? Now, I'd also want you to find it first in kelvins and then convert to Celsius. So here, this T1, so the small T1 would be the Kelvin temperature, and then the other one would be in Celsius. Okay, so again, you're going to just set up your relationship. You're going to solve for T1. Okay. And when you do that, now notice here, T2 was given in degrees Celsius. You cannot plug that in. You can't plug in that 0 degrees. You have to convert it to 273 Kelvin. Okay, you put in the two volumes that were given and then put in the temperature for T2 as calculated. You find that T1 then was 297 Kelvin. This is actually a way, if you didn't have a thermometer, it would be the really hard way to measure room temperature, but you could use it to measure room temperature. 297 Kelvin, and when they converted that, subtract 273, they found that room temperature was 24 degrees Celsius, which is pretty close to what we consider room temperature to be. 25 degrees C being, an optimal, quote, room temperature. All right, now you can relate Boyle's law and Charles' law, pressure, volume, and temperature, in something known as the combined gas law. Okay, so we already said that pressure 1 and 2 are related in this way, and then volume and temperature are related this way. Well, they both have a volume term, so if we kind of mash them together, then we end up with this form right here. Pressure, volume, and temperature. Now, why would we want to do that? Well, there is a chance. Remember, we said that if we relate only two things, all else being held equal, how realistic is that? That we are going to change just pressure and volume and the temperature is not going to change, or we're going to change just the temperature and volume and pressure won't change. Well, that doesn't always happen. It can be that two of the variables are changing at the same time. What is the effect on the third variable? That's what the combined gas law does. It allows us to put them all together. An example of that, we have a gas that starts out at 158 milliliters, and it's at a pressure of 735 millimeters of mercury and a temperature of 34 degrees Celsius. And what we're going to do is change two things. We're going to compress it from 158 milliliters to 108 milliliters, and we're also going to heat it up from 34 degrees Celsius to 85 degrees Celsius. We want to know what happens to that pressure. Okay? Reasoning through it in your head, we know that if we we decrease the volume. Okay, we said those are inversely related, so a decrease in volume should increase the pressure. And pressure and temperature, we haven't really looked at that, okay, but those are directly related. So if you think about it, you heat something up, gives it more energy, moves faster, increases the temperature. So increasing the temperature should also increase the pressure. So I'm going to expect my pressure to go up considerably here. But how do I actually do that? Okay, so I take my combined gas law here, and I solve for P2. Okay, so that's what they did in this step right here. They solved for P2. Then notice right here, very important, they converted their temperatures to Kelvin before they did anything else. Must be Kelvin. Gotta have Kelvin. All right, so now I take all those numbers. It's okay to leave millimeters of mercury. It's okay to leave milliliters. Those are all canceling out or leaving me with the unit I want, but I've got to have Kelvin. And when I do that, I find that the new pressure goes from 735 millimeters of mercury to 1250, 125, or 1.25 times 10 to the third, which you could just write as 1250 millimeters of mercury. It did indeed increase as we expected it to. All right, and then the last relationship we want to look at. All of those previous examples assume that I started with a set amount of gas. I'm not adding any gas to it. I'm not taking any gas away. The number of moles of gas remain constant. But now what happens if I change that? And let's just look at the relationship of the number of moles to the volume. All right, so if I were to take several samples of a gas at a constant temperature, so I've got room temperature and I've got atmospheric pressure, and what I'm going to do is have some way to, put it in a balloon so the pressure and temperature remain the same. I want to see how the volume of the balloon changes as I put more air in and take more air out. Well, common sense already tells us that if I take a balloon and I blow into it, I inflate it. It's going to increase in volume as I increase the amount of stuff in it. So again, I have this linear increase. As the number of moles increases, the volume increases. And this is related to Avogadro's law. So not only did Avogadro come up with the idea of a mole and the number of particles, he determined this number of particles, but also used that to relate number of particles to volume in a gas sample. All right, so we're assuming constant temperature and pressure here, and it's a direct proportionality, just like with volume and temperature. All right, so you blow into a balloon, gas molecules, exert their pressure, expand the balloon outward, increases the volume. Looking at a quick example of this one. If I have helium gas, 4.8 liters of helium gas, and I measure the number of moles of that gas, I find that I have 0.22 moles of helium. Now, if I want to increase the volume of that gas to 6.4 liters, how much more, how many additional moles of helium do I have to add in there? All right, this one isn't quite as straightforward as the others. I still have that initial relationship right here. Okay, so the volume of the gas divided by the number of moles of gas that I start with is equal to the volume divided by the number of moles I end with. All right, so if I solve for the number of moles that I'm ending with, that I'm solving for, I see that it's the ratio of the volumes times the number of moles I started with. Okay, so I find that N2 is 0.29 moles, but that's the number of moles that I need to end with, and I wanted to know how many more moles do I need from what I already have. So I have to take N2, which is the total that I need to end with, and subtract what I started with to find how many additional moles I have to add. So this one, a little bit tricky. You have to read the question pretty carefully there. But relationship, volume and number of moles, directly related. So that's a look at the aspects of a gas: pressure, temperature, volume, and number of moles, and how those relate one to another. Now, as I said in the last section, we will look at how we can tie those all together in something known as the ideal gas law. That will give you one overall formula that can be applied to all those cases that we just looked at. It can be used for any of those, and it can be used for additional stuff as well. We'll also look at something known as partial pressures when you have a mixture of gases, and the stoichiometry of gases. So that stoichiometry keeps coming back to haunt you. Anyway, we'll look at that in the next section.